Hi, in this video I'm going to be giving a demonstration of how to undertake dissolved organic matter assignment in AutoVectis. And normally you'd expect me to be processing ion cyclotron resonance or MRMS data, or possibly even orbitrap data starting from the transient. But in this case I'll be processing orbitrap data that was recorded as a raw file. As usual, we'll start with the AutoVectis splash screen. But this time, because the data came from an orbitrap raw file that was converted to an MZ5 format file using ProteoWizard's MS Convert tool, we'll import it into AutoVectis using the AutoQuis module. We can browse for the file that we want to process using this Browse button. Once the file is loaded, it's sent directly to the AutoPeaker peak detector. But we'll just use the default settings here, detecting peaks with a signal-to-noise ratio greater than 3. So now the peak list and the spectrum is open in AutoQuis. To export this to Autologous for assignment, we click up here. This dialog box is asking us where we want to save the process data, but by default it will be in the same folder as the original imported data was. And then that is automatically imported into Autologous. This is a single dissolved organic matter file, and the best way to process that is through the inference workflow. That means Autologous is going to look for the mass differences between all the peaks in this file. Where it finds peaks where the mass difference between them corresponds to the mass difference associated with a known homologous series, it will connect those peaks up into a network. For dissolved organic matter files, that network is normally so good that if you assign just a single peak in the file, you can cascade that through the inference network and end up assigning almost all of the peaks in the file very quickly. So following the inference workflow from the top, we don't need to import the peak list or the spectrum because that's already been done for us by AutoQuis. So we can jump straight to Create Connections Net. There are a variety of different ways of identifying the connections to use in your inference network. There is an automatic tool for identifying common mass differences across your dataset. Simple knowledge of the chemistry may help you identify useful connections. And we can train you in different ways that will suit your data. Or additionally, we supply connection nets that are likely to be useful to specific types of file. And that's what's open in this notepad. To get this into Autologous, we need to select Create New Cons from List. And then we just copy and paste the list in. At this stage, we could also modify how accurate the mass differences between peaks need to be in order to be included in a particular homologous series. Currently, this is set to 150 microdaltons, which is a normal setting for a file which hasn't yet been internally recalibrated, but isn't expected to be particularly badly calibrated. So we'll just use that value. And now we can build the connections net. So now we have a spectrum and a set of peaks that are connected through an inference network. Now we need a single peak that we can assign, and then we can cascade that assignment through the inference network to assign all the other peaks. These initially assigned peaks are known as seed peaks, and we can assign them using the Assign Seeds tool. You may already know the assignments of some of the peaks. But if you don't, we've included a tool to help you with this process. You can use the yellow cursor in the mass spectrum to identify a peak. Then you can use the Propose Formula widget to try and identify that peak. This tool uses a modified version of the Dromey-Foister algorithm to recommend potential elemental formulae for any given peak. You can set stoichiometric ranges for each element. You can change the mass range you search for and the type of ions you're looking for. And you can rank these assignments based on their mass error from the peak, their isotopic fine structure, or a unique MCDA algorithm that we've developed in-house. In this case, I'm going to accept the first hit that has only carbon, hydrogen and oxygen because I know that's the most likely assignment in a dissolved organic matter sample. Now at this stage, I could add other seed peaks by identifying other peaks in the spectrum, but for most dissolved organic matter samples, it's not necessary and a single seed peak will do. So all I need to do is click Accept Seeds. So now I have a spectrum where the peaks are connected in an inference network and a single one of those peaks has been assigned. So the next stage is to use the inference engine to cascade that assignment throughout the rest of the spectrum. The inference engine is really quite simple. It simply looks through its network of peaks to find those that are assigned and which are connected to unassigned peaks through a link in the network. Then it assigns those and keeps looping through until all peaks are assigned. The mass errors of the assignments are shown in this mass error plot. And don't be put off by the stripy nature of this. This is a feature we often see in orbitrap spectra where they've been assigned using a segmented calibration function within the orbitrap instrument, which has somewhat drifted. Autologists can largely correct for that later. And as you can see, the inference network assignment approach is quite robust, and it doesn't mind that the data wasn't perfectly well calibrated to begin with. In this display, we can see what fraction of the peaks has been assigned so far. And down at the bottom, we can see what connection type is currently being used for inference. If you want to stop or cancel the inference process, you can do that using these buttons. Once all possible connected peaks have been assigned, the system will detect that and turn the assignment rate graph green, and that's when you know the process is finished. You could now, if you wanted, modify the error limits or the stoichiometry limits and run the inference engine again. But we don't need to, so we can just close down the window. And now we can click View Results to view the results. So at the bottom we've got the mass spectrum where assigned peaks are shown in green and unassigned peaks are shown in red. And we can view the mass errors of the assignments on the Mass Errors by Mass tab. We can also view these in a heat map view on the Super Cool Plots tab. Here we can clearly see the influence of the segmented calibration function. And ontologists can do a pretty good job of correcting for that. On the Mass Error by Mass tab, I've already selected the Walker internal recalibration mode. And we also need to switch to the recalibration tab on the right-hand tabs. You need a high and consistent point density to get a good walking recalibration over a segmented function like this. So we'll select Get All Current Assignments. And then we can apply that recalibration. And we do this not because we needed it for the assignment, but because this kind of recalibration can be useful to reveal the true mass error of the assignments and to give you a better understanding of the mass error statistics. Currently, we've found only the monoisotopic peaks through the inference network. But if we move back to the main controls tab, we can select Find Isotopes to fit the full isotopic distribution of every assignment, including the fine structure if the resolution's good enough. On the Results tab, you can see the results are dancing around, and that's not because the Find Isotopes algorithm is randomly going through the data, it's assigning them in order of intensity downwards. And that's just in case one of the isotope peaks of a more intense peak was accidentally assigned as a monoisotopic peak through the inference network. This process is already quite fast, but I'll speed it up here just so that we can get on to the next stage. Once the isotopes are assigned, the system will automatically resave the data with a new timestamp. And now we can look to see if the isotope peaks fall within the expected mass error distribution. We can view the calculated isotopic distribution for any one of the assignments, and this will be shown on the ISO Model tab. To view an assignment, you should select the peak using the yellow cursor on the mass spectrum. This selected peak will then be the topmost peak in the All Peaks tab. To plot the isotopic distribution of that peak, or indeed any peak in this results table, you just double-click on the assigned formula. And then you can, for example, zoom into the isotopic fine structure in order to see how closely the theoretical distribution matches the peaks that you actually see in the spectrum. And this looks like a pretty good match. If we go back to the Super Cool Plots tab, we can view the results on a Van Crevelen diagram. And we can filter these assignments based on the elemental composition using the class formula control. So now we see only those assignments that contain at least one sulfur. On the flat view, we can see how these sulfur-containing formulae compare to the rest of the distribution. And you can use the cursor on this plot to identify individual components. I'll delete the class formula and then export the Van Crevelen diagram as a figure. There's a separate video explaining how to use this standard graph output module. But it lets you save many of the graphical outputs as figures for presentations or publications in PNG or PDF format. But you don't just have to save the output as figures, you can also export the assignments to, for example, Excel. And there are also mechanisms for saving the results to text files or even to SQLite databases to make them easy to combine into downstream chemometric workflows. So I hope this introduction to processing dissolved organic matter data using the AutoVectis suite has been useful. As usual, if you have any questions, you can contact us at autovectis@gmail.com, or you can speak to a member of the SpectraSwiss team directly.